This is part 2 of PIC Computing, A-Level Computing video number 24, looking at negative binary, and this time the 2's complement method of negative binary. Now in the first part of this video we looked at the first method for displaying negative binary in computers, which is known as sign and magnitude representation, and that, along with this second method we're going to look at in this part of the video, 2's complement, we should make a note at this point that these might be known as signed binary because they introduce the notion of having signs in front of numbers, whether they be pluses or minuses, positives or negatives. We have plus or minus signs introduced. Therefore, any standard binary, so just plain old positive binary, might also be known as non-signed binary. So if signed binary and non-signed binary are mentioned, then you should now know what those things are referring to. So this second method of displaying negative binary then, called 2's complement, it's probably a little bit more complicated, a little bit harder than sign and magnitude. When we're looking at this, we'll introduce another piece of terminology, which is the MSB, most significant bit. The most significant bit, when we looked at sign and magnitude, and the most significant bit is the leftmost bit in a binary number, represented either a plus or a minus, didn't it? Well, in 2's complement, the MSB does not represent either a plus or a minus. Instead, the MSB is the negative form of what it would be with standard non-signed binary representation. So if we have our base 2 number system, then the 1 to 8 isn't actually 1 to 8, it's actually minus 1 to 8. So in non-signed binary it would be 1 to 8, but in 2's complement it would actually be minus 1 to 8. So the MSB is actually negative, and always is in 2's complement. Now, if I bring onto the screen now a 2's complement 8-bit binary number, then what we do is basically the same as what we do when we're converting non-signed standard binary into decimal, is that wherever there's a 1 underneath, we use that number as part of our sum. So there's a 1 underneath at minus 1 to 8, so minus 1 to 8 becomes part of our sum. There's a 0 under the 64, so we don't use the 64. Likewise with the 32 and the 16, but we do use the 8, so we're going to add 8 into our sum. We don't use the 4, but we use the 2 and the 1. Now, those numbers across the bottom there added together come out at minus 117, and with 2's complement you're always going to get a minus number. That's because the MSB, the biggest value, is a negative value. Let's go through another quick example of that. So, base 2 number system, remembering that the MSB needs to be signed as negative. Example of a 2's complement 8-bit binary number. Only include the values where there's a 1. Now this one comes out at minus 44, and one thing to remember here is, well, just note we've used 8 bits again. You can do 2's complement with less or more than 8 bits, but in exams 2's complement only always seems to deal with 8 bits, so we'll concentrate on 8 bits in our examples. Now we could keep on practicing those, they are quite easy to do. Unfortunately, you're likely to be asked about doing the conversion the other way round when it comes to questions in the exam on 2's complement. So let's take a look at an example of a past paper question. Here we go. Express the denary number minus 53 as an 8-bit 2's complement binary number. Notice it says 8-bit, and it's most likely to in your exam. We've never seen a question that doesn't deal in 8 bits when it comes to 2's complement. So it's worth 2 marks. So it's minus 53 that we need to convert into 2's complement binary. We mark down our base 2 number system. But note, when I do that, I haven't put a minus sign in front of my MSB. There's a reason for that. What we're actually going to do is just write down the binary for positive 53 and not negative 53 at first. So positive 53 in binary is this 00110101. The next thing that we do is we do what's called the complement of each of those binary values. And the complement is basically the opposite. So if it's a 1 here, we'll write a 0 underneath. If it's a 0, we'll write a 1. And that's known as the complement. And this is where we start to get the term 2's complement from. So it's a 1 here, so we're going to put a 0. It's a 0 here, so we're going to put a 1. It's a 1 here, so we're going to put a 0. It's a 0 here, so we're going to put a 1. And we do that all the way along. So 1 here, 0, 1 here, 0, 0 here, 1, and 0 here, 1. Now, once we've done that, we've actually completed what's called 1's complement form. So we've just taken the complement, i.e. the opposite, and marked all of those down. To get 2's complement, which is what we're after, all we do now is add 1 to our 1's complement form. So we do that. Now that's going to be quite easy for this example. If we remember our truth table, when it comes to adding binary, we know that 0 and 1 is 1. And then all the other remaining bits in this 8-bit binary number are going to be the same as what they are on this line here, because we've just added 0 each time effectively where there's blanks. So that's going to be a 1, 0, 1, 0, 0, 1, 1. And now we have our 2's complement form of the denary minus 53. So that is our answer effectively on that bottom row. They can be a little bit more difficult than this example where we're converting minus 53. So if we take this as an example, we're actually just converting one number more, as in minus 52. This example is slightly harder. Base 2 number system, positive 52 in binary. 1's complement, just do the opposite each time, easy enough to do. Add our 1 to get 2's complement. It's a little bit more difficult because we are adding 1 and 1 here, which, if we remember our binary truth table, is 0 carry 1. So we're actually doing a bit of carrying here, which makes it slightly more complicated. Again, 1 plus 1 is 0 carry 1. 0 and 1 is easy enough, it's 1, isn't it? And then it's just the same values as above going along wherever there's a blank underneath. And then we've got our answer to that one. So slightly more difficult, but only because we're having a carry as part of our binary addition. Whoa, we're getting a little bit more advanced here. This is the most complex question that I've seen in an exam paper on 2's complement. It's worth 4 marks because it is a little harder. Using 8-bit bytes, describe how 2's complement can be used by a computer to calculate the answer to 93 take away 51. How are we going to show this? Well, you might tell the examiner that 93 minus 51 is the same as 93 plus minus 51, and then you'd show the binary equivalent of 93. You'd show the 2's complement equivalent of minus 51, so you'd have to go through that process that we've just looked at of converting 51 into binary, put it into 1's complement, and then put it into 2's complement. Then you'd add those two binary values together, the binary equivalent of 93 and the 2's complement equivalent of minus 51. You'll actually get something called an overflow when you do this on this particular example, where it carries from 8-bit binary number, so the use of 8 bits, into actually 9 bits. So we get what's called the overflow. Now when you get the overflow, you actually ignore the carry. And that means you ignore the MSB, the very first bit. So you come out with your answer, which is 00101010, and you can double check that. 93 take away 51 is 42 in denary, and the binary equivalent of 42 is the same as the answer we've got. So that's right. Now that is a bit more advanced. What you should do now is try some of the easier ones and possibly the last one, which is a little bit harder. Number 5 might be a bit different from what we're used to, but give it a go anyway. And that's all good practice for you, ready for your exam. Good luck.